Hello, welcome to the exida webinar. Today we're going to be talking about how do I get a SIL level for my PLC. Now effectively we're going to be talking about 61508 certification, but we'll get into that in some depth. My name is Bill Goebel. When I started my career, I was in new product development. Add more products, an original OEM automation manufacturer. In those early days, I loved doing electronic design, microcomputer design, embedded software. And then I went to the dark side and became management and marketing. I was really pleased a few years later when I had the opportunity to help co-found exida, the company I work for now. You can see we were founded in late 1999. Think about that calendar time for a moment, because we're coming up on our 20th anniversary, which I think is just very exciting. exida is a company that has three fundamental business units. We have one unit that does engineering tools, and we have tools for OEMs and tools for systems designers. We have one group that does system lifecycle services, and we have a third group that does certification and assessment. Today, we're primarily going to be talking about the exida certification group, and the exida certification group does primarily functional safety and cybersecurity certification for personnel, for products, for systems, and even for engineering processes. We started that particular business segment in about 2004, and we didn't realize it, but by 2014, we had become the global leader in functional safety certifications. We didn't realize it until ARC Advisory Group did a market study and showed we had about 2/3 of the entire functional safety certification market. And even in the logic solver category, where the very first certifications were done in 1982 by TUV Product Service, which is now called TÜV SÜD. Even in that category, exida has overcome a 20-year head start to become the market leader. As you can see in the slide in the lower left-hand side, exida is the strong market leader, but we have strong competition from TÜV Rheinland, who's right behind us, and the other active companies doing functional safety certification are TÜV SÜD and TÜV Nord. exida pioneered automation cybersecurity and remains the clear world's leader in automation cybersecurity certification. We're very proud of our impact in these new areas. Now, what is the SIL business all about? What is a SIL? In many industries and applications, automatic protection systems are designed to recognize dangerous conditions and take action to mitigate the danger. This has been going on for decades and decades. Of course, when it came time to use complex electronics and software for this purpose, there was a lot of controversy. A large group of people met for many years and created a standard on exactly how the engineering should work for such important systems. And the engineering to create these systems is now done per a specialty field called functional safety. The basic safety standard defining this field is IEC 61508. Now, what is the SIL business? The 61508 standard has a definition for safety integrity level, and that standard defines 4 levels called SIL. You can see 1 is at the bottom. It's the least safe, and it has a risk. It's characterized by a risk reduction factor between 10 and 100. As you go up in the numbers, you can see the risk reduction factors drop by an order of magnitude. That means the safety integrity gets better by an order of magnitude up to SIL 4, which has the highest specified level of functional safety. And many of the people on the committee believed that SIL 4 is about as good as you could ever do with any automatic protection system. And actually, I completely agree. Well, if we have this thing called SIL, and we know what it is and we know what the standard is, well, what is this thing called SIL certification? It's third-party expert attestation. I spotted that word in the standard for product certification programs. Thought it was kind of fancy, and I kind of like that word, attestation. Anyway, it means you get a really good expert to audit and attest that the subject of the certification meets the requirements of the standard. What do they look at? Well, we do a detailed analysis of the engineering and test processes. Objective, determine the design quality and cybersecurity resilience. We do a detailed analysis of the hardware design and the design margins. And that results in, if you have a good tool and a good method, a prediction of random failure rate in all failure modes. We do a detailed analysis of the software design, automatic diagnostics, and any response mechanisms designed into the product. And lastly, there's a detailed analysis and testing to show safe, correct operation of the product and to show sufficient cybersecurity testability. As you might guess, or as you might see right away, this is not like your ISO 9000 quality standards, which originally concentrated on manufacturing procedures and manufacturing process quality. IEC 61508, on the other hand, is not focused much at all on manufacturing. It is focused on the design process, and therefore the quality of a design. Who does SIL certification? Well, certification programs have been established by private companies and some governmental bodies around the world. But what's important is that any organization doing certification work should be accredited for their field of work. In the United States, for example, exida was accredited by the American National Standards Institute, ANSI. ANSI is a member of the International Accreditation Forum. And that means all the different accreditation bodies in the world compare notes and to set up common criteria, and they have a multilateral recognition agreement which assures the global acceptance of any certificate that's part of this program. So this is a nice infrastructure that has been set up to accredit and validate certification bodies like exida. Okay, we have this nice infrastructure. We're working to a credit per 61508, but what is 61508? IEC 61508 has two primary goals, and I hope these are pure common sense. Many of the requirements in the standard are directly aimed at making sure the product works correctly. We want it to be reliable. We want it to work and not fail. Well, that's a good thing, but there's one more dimension to it, which is very important. We want to make sure the system will fail in a predictable, safe manner, which means the designers must consider the impact of failures and design for fail-safe response. Every requirement in IEC 61508 is intended to achieve these simple goals. Now, system designers have to look at three things when they're selecting the equipment they use. Equipment like your PLC, or your gas analyzer, or your motor controller. They have to look at a thing called systematic capability rating. They look at a thing called architecture constraints, and they look at a probability of dangerous failure calculation. What are these things? Well, systematic capability is a measure of design quality, justified by a PLC customer based on prior use experience and documented field history, field operation history, or alternatively IEC 61508 compliance. Architecture constraints is just kind of a fancy word for sometimes there are minimum levels of redundancy. You're required to have a certain amount of redundancy in some designs. And lastly, this probability of dangerous failure calculation is interesting, but the key is it must be done with realistic failure rate data for all the components in a system design. Now, what's that mean then to an original equipment manufacturer trying to get a SIL rating? It means you must achieve a systematic capability rating done by detailed analysis of the engineering and test processes, which are done to determine design quality and cybersecurity strength. It means you must meet certain requirements from 61508 for architecture constraints using a combination of automatic diagnostics and redundancy. And lastly, it means that the OEM must do a detailed analysis of the hardware, resulting in a failure rate prediction for all failure modes. You have to provide numbers that system designers can use when they're designing their system. All right, what is this systematic capability? What do you have to do? Well, remember, we're trying to measure design quality. You have to have engineering process requirements that are based on good quality systems and good software engineering techniques. Those processes must be defined, documented, and audited. And the level of detail and the rigor increases with each SIL level. The process requirements for SIL 1 are not as strong as the process requirements for SIL 2, and so forth in SIL 3 and SIL 4. Every process has to have a defined set of steps. For each step, what input documents and input information is required, what output documents are generated as a result of that work, what work is done in each step, and what error checking techniques are used to make sure the work in each step is done properly. And if you think about it, that makes sense. We're trying to make sure the product works correctly, and we don't want any residual design flaws. A big part of the process is software engineering. Now, for those of you who have not heard about it, I remember software engineering, reading about software engineering in the mid-1980s. And it was a series of engineering techniques designed to increase software design quality and reduce design mistakes. Well, that sounds like 61508, which increases the probability that the automatic safety function will perform correctly. So software engineering is all about correct operation. Now, of course, software engineering also should reduce project lifecycle schedules because it reduces rework, and it should reduce product development cost and gets new products to market faster. And I remember reading a lot of studies about this in the 1980s, and I have to say it was quite interesting. The bottom line for this webinar is that Part 3 of IEC 61508 was written full of requirements based on fundamental software engineering principles. But you got to have a good process. In other words, I like to say you got to have some playground rules. Now, I don't mean to insult software developers. I think of embedded software development work that I used to do, and I loved going to work. So I can almost think of my work as a playground. Yeah, believe it or not. But you got to have rules in any playground. And the software development process must describe those rules and have enforcement mechanisms in place. Yeah, adult supervision is required. Systematic capability, good engineering process, hardware and software. What about architecture constraints? That's where we have to meet 61508 requirements with a combination of automatic diagnostics and redundancy. I'll just briefly describe what this is all about. The 2010 version of 61508 had two alternative mechanisms to meet architecture constraints. Route 1H, which uses the upper chart, and Route 2H, which uses a set of rules characterized by the lower chart. And you can see the lower chart's a bit simpler, and Route 2H can be used if you have a good traceable field failure rate based mechanism for your failure rate predictions. And if you don't, then you have to use 1H, which is still calculated from the failure rate predictions. But the bottom line is Route 1H doesn't have as much depth and precision required on the failure rate prediction mechanism. But both of these methods, 1H and 2H, depend very much on failure rate predictions. And the bottom line is redundant hardware may be required for the higher SIL levels. Systematic capability is your engineering process. Architecture constraints is automatic diagnostics in combination with redundancy. The last thing is we want to talk again about the importance of this failure rate prediction, because what we're trying to do is do a detailed analysis of the hardware and the design margins, resulting in a random failure rate prediction for every valid failure mode of a product. Now at exida, we use the FMEDA methodology to accomplish this. And FMEDA stands for Failure Mode Effect and Diagnostic Analysis. It's a method that was created in the late 1980s by engineers that are now at exida. And it is a study of design strength. Better, stronger designs have lower failure rates. Also, you must consider then the components and their application parameters. The FMEDA technique requires a component failure rate database with failure rates and failure mode distributions for all of the components. And typically that's done as a function of application and environmental profile. So the component database has a lot of data in it. If you have a good component database, you can use the FMEDA technique to predict failure rates, failure modes, diagnostic coverage, which is a measure of diagnostic quality, useful life, and even proof test effectiveness for each subsystem. The whole FMEDA method was specifically created to allow practical implementation of functional safety compliant products. At exida, we have a specific tool developed for doing FMEDAs called FMEDA-X. It has all the features we need to pretty cost effectively meet all the functional safety standards. And we do make that tool available to our own analysts and our competitors. And some of our competitors are using the exida tool. But the tool's got to have that good failure database that I talked about. Early on, there was a lot of debate about what to use. And what's important is you use a database that produces realistic predictions for the particular application. To make sure that happens, at exida, we use what I call a closed loop technique, where we gather up field failure data from manufacturer's data, from exida's SIL stat failure rate collection software, ISPM, another failure rate data collection software, OREDA, the Offshore Reliability Equipment Database Association, and we compare the OREDA published data with field failure data from other sources, and we compare the total failure rate for a product to the FMEDA result. And if you have a good method, the proof that you have a good method is when the data matches. If the data doesn't match, you have to dig in and find out why, and that usually results in updating a component failure rate, creating a new part, updating the failure mode distributions based on the actual data received, update and feeding that back into the component database. And you can see down here in the lower left-hand portion of this drawing, there's a nice closed loop that eventually reaches steady state. It works pretty good. Of course, it's a lot of work and it takes a lot of time, but it's the only way we could think of to do it. The FMEDA-X tool does have electronic components, mechanical components, and sensor components, with many new technology components using the latest semiconductor technology. Unfortunately, we're able to work pretty closely with several semiconductor companies to keep our database way up to date. And at this point, this database has been validated with over 350 billion unit operating hours of equipment data from multiple applications and multiple environments, which is pretty nice. Now, we talked about systematic capability, architecture constraints, and probability of dangerous failure calculation. And those three categories tell you a whole lot about 61508. We do detailed analysis of engineering and test processes. We do a detailed analysis of hardware in order to determine failure rates, which are used to meet architecture constraints. And then, of course, we provide the failure rate data for system designers to do probability of dangerous failure calculation. And I kind of misled you because there is a little bit more to it. There is a need for an audit of quality procedures. There needs to be manufacturing audit, unless that's done by someone else, another company, which may be the case. And of course, the objective there is to make sure that a given design can be replicated safely. And lastly, there's a product documentation audit. A typical certification project starts out at a very high level. And you can see in the middle of the drawing a diagonal box that says gap analysis. That's a very informal audit that's done at a high level to help companies figure out how good they really are. Sometimes the gap analysis indicates, boy, you're really close. Your process is good. You're really close to meeting SIL 2 process requirements right now. And of course, if that's the objective, that's good news. If they don't meet that objective, they work on the gaps, they upgrade their procedures, they do specific training for their people, and finally, at some point, they're ready to go for a full audit. Exida uses a concept called the safety case, where we have documents listing every single requirement from 61508 and any other referenced standards. So we go through for every single requirement and make a judgment as to whether the company and the product meet each requirement. And you write down an argument as to how you meet that requirement. And for every argument, you must have evidence showing that the argument is valid. Requirement, argument, evidence. And finally, when we get all the requirements filled out and we take into account the specific design documents of a product, your FMEA, failure mode and effect analysis, the FMEDA is evidence, software HAZOP might be evidence, communication protocol might be evidence, and all the evidence goes into the safety case. When the safety case is complete, and it feels every requirement has been satisfied, the safety case is audited and a certificate is issued. I see a question. Thank you, sir. Raise a point stressed by one of your colleagues in his blogs about mission time. How is it considered in FMEDA, especially for corrosion for EX, which takes a long time? Mission time is a variable used in the probability of dangerous failure calculation. Another variable that's important, which I mentioned during the FMEDA, is useful life. In the world of 61508, we characterize the bathtub curve of failure rates with a solid line on the bottom, a constant failure rate, and a vertical line at the end of the bathtub called useful life. And the intent is that a system owner operator must replace all equipment before the end of its useful life. Often, corrosion is taken into account two different ways. First of all, it may impact useful life. And secondly, depending on the rate of corrosion, which may be a variable as a function of different corrosions in the atmosphere, it does impact the failure rate during the useful life. But we make an assumption that that's constant, and usually that's a pretty conservative assumption. I will tell you that in the exida component database, corrosion is a variable that is considered, and there is a series of different environmental profiles with different corrosion atmospheres suggested based on I can't remember whose standard that is, IEC or ISA. I think it might be ISA. Let's say for now it's an ISA standard. But if you're interested in those operational profiles, and in particular the corrosion specification, we have an entire webinar on the FMEDA process, and some of those profiles are shown during that specialty webinar. Now, you saw this certification project, and you saw that it might have looked tough. It's okay. I want you to know that many have been successful. Hundreds of automation manufacturers have successfully achieved IEC 61508 certification using the exida process, which we think is tougher than anyone else. Well, we know it's tougher than everyone else. And yet, people still pass. And here's two examples that have achieved a SIL 3 systematic capability, which means they have a pretty good process in place. Nothing's perfect, but it's really good. So it can be done. You can do it. Let me be positive with you. You might ask yourself, why are you really interested, and is it worth the trouble? Well, we have to ask the question, why does anyone even care about SIL? In the process industries, the 61508 derivative standard, IEC 61511, specifies 61508 certification as one of the ways to justify equipment selection. And it's really simple and really easy. And therefore, what we see happening is anyone who is interested in saving engineering hours and getting their equipment justified rapidly, they will be using 61508 certified devices. Another way of saying it is that many of the designers want to dump the problem on the vendor. And of course, that's been going on for decades as well. Many operating companies want to reduce spare parts types, and they use certified components for everything in the control system, the automatic protection and the control. Many petrochemical companies are now using 61508 certification as a measure of product design quality, which I believe it is. And a complete 61508 certification program provides system designers with all the information they need to do their work, although some certifications don't provide that information. And lastly, I've seen a couple instances recently where corporations and their insurance companies are starting to require products with 61508 certification in safety applications for those who want the special discount ratings, which means save money. That's always a good thing. The bottom line is you can do it. Many of the world's leading safety PLC manufacturers have successfully passed the exida certification program. And at this point, we're very proud that the exida certificate has become the most requested certification in the process industry safety function market. So if you're going to do this, give us a call. So when your customer asks, do you have an exida certificate? You can say, yes, sir. Anybody else have any questions you'd like to ask? Thank you. I see another question. I saw a blog on the exida website where you talked about whose failure rate is right, exida or TUV Italia. You never answered the question. Which one is right? Okay, you're right. I didn't answer the question. I guess the real answer is I don't like to criticize competition, but it all depends on the assumptions made and the information provided. We have a nice detailed explanation of that in a series of 4-part videos, which are available on YouTube and some of our white papers. But the bottom line is failure rate varies from site to site for the exact same manufacturer model number. Failure rate varies as a function of operational profile. And it's very possible the very low failure rate numbers are valid for, let's say, laboratory conditions where perfect maintenance is assumed. But in exida, we have a very comprehensive definition of failure, including all failures that were real and might contribute to a dangerous condition. We define the FMEDA predictions for a given set of operation and maintenance characteristics. And we have a full model to predict different failure rates as a function of different operating conditions. And of course, all those are embedded in one of our engineering tools called Excellentia. So anyway, I think the problem was, of course, the exida failure rate was like 400, and the other company predicted a number like 40. And everybody's thinking, well, the other product must be better. Well, it appears to me as if the other product was evaluated for laboratory conditions and perfect maintenance, whereas exida takes a far more realistic approach and evaluates and estimates per real operating plants. Sorry if that was a long answer. In order to have a SIL 3, let's just check this out. Does a safety PLC have subsystem components that are also SIL 3? It's a common interpretation, at least at exida, that the architecture constraints are applied across an entire safety PLC, not each separate component or subsystem. You don't have to have architecture constraints for an input circuit an input processor, a communication bus, a main processor. It's the whole PLC, the whole element that counts. All the pieces do need to have a SIL3 design process in place. And lastly, of course, the failure rates are different for each subsystem, and the system designer calculates the SIL level of his system design. Getting lots of questions. Can you please elaborate? Oh, yeah, good question. On the differences and usefulness of FMEA and FMEDA reports. FMEA is typically a higher level it's a qualitative or semi-quantitative approach, failure mode and effect analysis. It's very useful in early design phases, but it's not useful for generating particular failure rate predictions. The FMEDA goes down at least one level, typically one level deeper, to the component level. So if we're talking about an actuator, we talk about the structural member, the spring, the seals, the pistons perhaps, the bearings, and we look at every part, how that part can fail, and how that contributes to the success or how that contributes to the failure of the product, like an actuator. That is full quantitative based on the component database. So FMEDA is done for detailed, quantitative, failure rate, useful life, and diagnostic coverage prediction. FMEA is typically qualitative and is intended to detect architectural type design flaws. Both are valuable tools in the certification process. Both techniques can be used to meet requirements from 61508. That was a good question. Thank you. I will say that if you have any other questions, don't hesitate to send an email. We'll be happy to answer you, probably asynchronously. In other words, we don't monitor email all the time. And I can answer it, or I can pass it on to one of our other experts. And we're most happy to help you. If you feel you are ready to go get a SIL for your PLC, please give us a call and let us give you more information. I want to thank you all for your time. I was targeting to be ended by 4:45 EDT, and we're basically right on schedule. So I thank all of you for your time. We have lots of additional recorded webinars and white papers. Please help yourself, they're all free. Thanks again for your time, and I hope to hear from you again. Goodbye.